I forgot something very important in the last video. The problem actually asked us for the magnitude and direction of the B field, and I only found the magnitude. So I got only partial credit on my test, so do as I say and not as I do. But with that in mind, let's go ahead and investigate what the direction was. So we have this long cylindrical wire, and using the right-hand rule where we point our thumb in the direction of the current, our fingers give us the direction of the B field. So the B field should go around like this relative to the current pointing upward. And in retrospect, I think the picture that I had drawn for this problem was actually wrong. I had the B field pointing that way, which means the current should have been coming outward like that. So this would be a way to mark which direction the B field would be pointing for a long straight wire. And maybe this would be a good opportunity to discuss where that form of the right-hand rule came from, and just more generally, why the magnetic field is circular surrounding a wire. So if we picture some current-carrying wire and some differential bit along that wire, some infinitesimally small piece, then the magnetic field due to that little current-carrying piece is given by the Biot-Savart law. At some distance r away. And if you recall, whenever we first defined electric fields, the definition looks something like this. And you can almost think of the Biot-Savart law as an analogous definition for magnetic fields to the electric field for a point charge. With the important difference that there are no such things as point charge-like objects or magnets. There are no magnetic monopoles. So rather than getting an electric field from some point charge, instead we get some differential bit of magnetic field from some differentially small bit of current, because currents are what give rise to magnetic fields, in the same way that charges give rise to electric fields. Which is why whenever we want to find the total magnetic field from the whole wire, we have to integrate this entire expression. But still there are some similarities. For example, here's a constant out front, here's a constant out front. Both of them are proportional to 1 over r squared. And the electric field is proportional to the charge, where the magnetic field is proportional to the current. The most noticeable difference is that this vector expression is given in terms of a cross product. So now let's look at this picture, but let's look at it downward at the wire. So now our current is coming up out of the board, and then this R points off in some direction like this maybe. Okay? So the differential bit of the B field that comes from this is given by a cross product with S, ds, which is coming straight up at us, and R, which is pointing out like this. And the right-hand rule tells us that dB points 90 degrees to both, like this. But that's also true for if we chose this as our radius, we would get a B field that looked like that. And if we chose this for our radius, the B field would look something like this. And so on and so forth. And when we consider all of those counted up together, we're going to get a circle that hopefully is much more circular than the circle I just drew. But that's why the magnetic field sort of swirls around in a circle like this. It's orthogonal to both I, the current, and R, the radius at every point. And that's why this form of the right-hand rule, your thumb points in the direction of I, and your fingers give the direction of B, is what gives us the direction of magnetic fields created by current-carrying wires. Okay, let's look at our last problem. This time we're given a long solenoid, we're told how many turns it has, how long it is, and what strength of magnetic field it produces on the inside. And we're asked what current is required in each of the windings for that to occur. So here's our solenoid. It has 1,000 turns. It is, let's see, 0.4 meters long. And the B field on the inside is 10 to the negative 4 Tesla. Now, recall that the magnetic field for a solenoid is given by mu naught N divided by L times the current I. But before we just use this expression to solve the problem, let's see where it came from using Ampere's law. First of all, let's cut the solenoid down the middle and look at a cross-section of it. So each of these that I've drawn is a bit of the wire. The coil would look something like this as it went around. By convention, the current is going into the page on the top and out of the page on the bottom. So what I've drawn is the current. Next, I need to draw an Amperian loop, and I'm going to decide on a rectangle of length L. I chose a rectangle because the cosine theta term inside the dot product will drop away. We'll see how that happens in just a second. Now, by the right-hand rule, we can see that the B field vectors inside will point to our left. Now let's go ahead and write an expression for B dot ds. B dot ds is B ds cosine theta. ds is a little bit of this Amperian loop. So you'll notice that ds is right in line with the B field, and that means the angle between them is 0 and the cosine is 1. So B ds. And now we can go ahead and perform the integral. Integral B dot ds is equal to B times the integral of ds from 0 to L, which is just B times L. Now remember, the right-hand side of Ampere's law says that that's simply equal to, this integral is simply equal to mu naught times the current enclosed. And how much current was enclosed? Well, for our loop, however large we drew it, it looked something like this, where we had some number of wires enclosed by the loop, and each of those is carrying the current I that's going through the solenoid. So the total current enclosed is going to be N times I, N copies of that current I. And so now we can equate these two and solve for B. That's BL is mu naught Ni. That's a typo. There should be a mu naught right there. And then we get that B is equal to mu naught N over L times I. And this, by the way, is not a result that you'll have to derive each time to solve the problem unless you're asked for it specifically. You can just go ahead and use this equation to solve problems. But go ahead and do it once just to convince yourself of how it works using Ampere's law. Equation for current. So we'll get BL over mu naught N. L comes to the numerator, mu naught and N go to the denominator. And using a calculator, I got about 0.032. 0.032. And this is a current, so we would hope that the units come out to be amps. And so let's check and make sure that they come out correctly. Teslas cancel with Teslas. Meters cancel with meters. Turns, 1,000 turns is just a number, and we get 1 over amps, which is amps.